Okay, so up next is Yutaro Yamada, a research scientist at Sakana AI working on LLM agents, open-endedness, self-improving AI, and automated scientific discovery. He was trained in statistics and data science at Yale. Among others, he worked at Meta and the Allen Institute for AI. Today, Yutaro will share what it takes to move from human-led AI research to self-improving AI. Please welcome Yutaro Yamada.
Thank you for the introduction. So today I'm going to be talking about, so the title of my talk is From AI Scientist to Self-Improving AI. So this is divided into two parts. The first part I'm going to talk about AI scientists, and the second part I'm going to talk about self-improving AI. And a lot of the stuff that I'm going to discuss today is a joint work with these amazing collaborators, Robert Lang, Zhong Liu, Sharon Hu, Jenny Zhang, Chris Liu, Jacob Forrester, Jeff Clune, and David Hall. So to set up the scene, I sort of want to kind of take a step back and reflect on what we've seen in the last decade, especially in the generative AI field. So if you look at the image domain, we started with VAEs and GANs, variational autoencoders, and generative AI, networks for image generation models, and now we have these, diffusion models that can produce really photorealistic images. If you look at the text domain, we started with sig-to-sig model, and then transformer models came. And then now we have these large language models from these frontier AI labs that can produce really complex reasoning traces and complex reasoning abilities. And for the video domain, especially in the last, I guess, 2-3 years, I think we also see a lot of progress, especially in the video quality, thanks to mostly large-scale data pre-training and architecture innovation. And now we see things like VO3 or like Sora 2 that can produce really hyper-realistic video data. And now if you look at the science domain, so like in 2021 we saw AlphaFold from Google DeepMind that just won Nobel Prize in chemistry last year. This was sort of like a prediction model that can predict the 3D structure of protein just based on sequence of amino acids. And there are things like ESM3, which sort of like goes beyond just protein folding prediction, but tries to predict the function or properties of these proteins. And these are really amazing progress, but this is sort of like a part, automating like a part of research processes. And what we wanted to ask was like, can we automate like the entire research process, like from end to end? And this AI Scientist V1, which was released in August of 2024, was sort of like our first attempt towards that goal. But I think this is, especially in the science domain, this is still like the beginning of something that could be bigger. And as we've seen like in the other domains in image and text and videos, I think we could there could be improvement over time. And I think collective effort from open source communities for democratization would be critical. So LLMs or large language models are have been used in a lot of places, especially in machine learning research, to automate parts of this research. This often comes with the style of evolutionary search, where LLMs are used to sort of generate candidate solutions, and they get updated, and they're sort of stored in a database, and then continuously sort of like keep innovating these candidate solutions using foundation models like LLMs. And this style of evolutionary search has many applications in machine learning. For example, for designing loss functions or objective functions, or if you look at the reinforcement learning domain, it can be used to design like reward functions. And you can also go like go like a little bit of meta by thinking about designing LLM agents itself by using this sort of evolutionary search algorithms. But science is not just discovery of individual components, and it's about basically from like coming up with like a good problems to focus on, and coming up with hypotheses, discussing with colleagues, and running experiments. And if you get some nice results, you could try to write a paper and then submit it to a review, and then you get feedback. You get feedback, and once you have this review process is done, you go publish your paper, and then knowledge sort of disseminates on the internet through blogs and social medias. So the question we wanted to ask again was, can we automate this entire research process with some sort of AI systems? So the grand vision here is if we can have some sort of AI systems that can continuously innovate and accumulate, discover knowledge, just like how human societies and human research scientist communities are doing right now. So here's an overview of the AI Scientist V1. This was a template-based research pipeline, and this was template-based in a sense that you had to we had to provide like human-authored code template at the beginning, sort of as a seed for this run, for like a run of this system. So it has three parts. There was this ideation part, and then experiment iteration part, and then the paper write-up part. And all of these stages were sort of conditioned on the idea that was presented in the code template. So, for example, in this idea generation, like the ideas that are generated in this stage were sort of derived from the idea that was present in the initial code template. So to evaluate this system, we selected 3 subfields in machine learning: 2D diffusion, which is sort of like a simpler version of like a synthetic version of image data, and for NanoGPT, and the second one was NanoGPT, which was sort of like a mini library that people use, like transformer-based for training small transformer-based language models. And the third domain was grokking, which is an interesting phenomenon in machine learning where if you continuously train on the training data set, even after you get 100% accuracy in the training data set, if you sort of like continue training, you kind of get this sudden grokking moment where you see a sudden increase in test performance. And this sort of like shows like this continued training can kind of unlock this just like a sudden generalization in this training. So this is an overview of the results of the AI Scientist V1 system. We generated about 50 papers using, in each of the subdomains we chose, using 4 different frontier models. So we see that the Sonnet 3.5 performs the best, and Llama 3.5, which is, I believe, like 400 billion parameter models, performs the worst. But what's interesting here is that DeepSeek model, which is an open source model, also performs relatively well compared to Sonnet 3.5 or GPT-4o. But the AI Scientist V1 system has several limitations. For example, as I was alluding to, you had to rely on a human-authored code template as a seed. And the execution planning was sort of linear in a sense that it only sort of like keeps track of a single chain of operations of improving and debugging. And the system didn't support parallel execution of these experiments. And we didn't use a VLM or visual language model anywhere in the pipeline. So in the the V2, the version 2, we try to sort of like address these limitations. This is an overview of the AI Scientist V2 system. It's very similar to what we saw in the V1 system, but we basically try to generalize every stage. For like idea generation, we try to have like more like a grand style proposal idea generation. And then for the experiment stage, we use tree-based search algorithms, which I'm going to talk a little bit more in the next slide. And then paper write-up stage was based on more powerful reasoning model. So it didn't need to rely on like say section by section writing. And now this is more like a one-shot writing. So now I'd like to get into like the details of the experiment pipeline. So the in the V2 system, we use this tree-based approach. So each node in the tree sort of represents a single experiment run, and then this has like a 4 stages of these experiment stages, and we introduce an experiment progress manager that kind of guides through these different stages, which is also based on LLM. And so the stage 1 was a preliminary investigation to get a working prototype or working sort of like code prototype. And stage 2 was hyperparameter tuning to get a nice baseline. And stage 3 is the most interesting part, where you sort of actually execute the research agenda that was provided from the idea generation stage. And stage 4 was evaluation studies. So yeah, and then each node in the tree is a single experiment run that contains like the plan and results from numerical results after you run an experiment, and error logs if there is any, and visualization and visual these feedback from VLMs on these visualizations. So there are also specialized nodes. For like specialized tasks like hyperparameter tuning or ablation or replication nodes for statistical rigor and aggregation. So this tree search sort of like balances between like exploration and exploitation in some sense, where it tries to explore these nodes in parallel, where the exploitation stage is sort of like trying to expand more on the promising nodes, and then he also tries to fix debugging. Debugging stages is sort of like try to debug these unsuccessful nodes. So how well does this system actually perform? So to test this, we sort of like try to put it into like ultimate test, which is like the peer review process that human scientists also go through. This is a snapshot of one of the papers, one of the generated papers that is entirely generated by the AI Scientist V2 system. And we submit this paper along with 2 other generated papers to one of the workshops at ICLR. And then we received scores of, for this particular paper that we show here, we received scores of 6, 7, corresponding to 1 accept and 2 weak accept. This was placed as like the top 45% of all submissions at this workshop, where about 70% of all submissions were accepted. So to run this experiment, we maintain full transparency with the leadership of ICLR as well as the organizers of this workshop, so that they know that we were running this experiment. And crucially, the review process was blind in a sense that reviewers knew that like some of the papers that they review might be AI generated, but they didn't know which ones they are also able to sort of like opt out from this experiment if they don't want to review any AI generated papers. And we had a IRB with from the University of British Columbia, and we also had a pre-agreed plan that any sort of like accepted AI generated paper would be withdrawn automatically after the review process, but before like official publication. And this was to sort of avoid any sort of like a controversial stuff before sort of like establishing community norms about AI generated science or AI generated papers. So this workshop, I guess, acceptance was a milestone, but we also need to be realistic about the limitations and capabilities of the current system. And just like any other large language model, this AI Scientist V2 system also has an issue of hallucination. For example, in one instance, in the accepted paper, there was like hallucination of like citation where they miscredit or for say LSTMs for they instead of like citing Schmidt-Huber, they cited Goodfellow, for example. And we like human scientists, we don't want to make this kind of like a simple mistake. And in another case, for the papers that were submitted to the workshop but not accepted to the workshop, there were instances where the system sort of discusses the results that were not in the paper but exist in the sort of like experiment logs. So this system still has issues of this, hallucination and sort of like limitations that stem from reasoning capabilities from LLMs, which makes it difficult to adhere to, always adhere to, like the experimental evidence that was collected during their run of experiments. So beyond specific issues or errors, now I would like to sort of like talk about more like a broader challenges that we as a community might face with sort of like these new AI technologies. One is transparency and attribution. So we believe in like providing transparency as much as possible, especially related to this AI generated papers or AI generated science. And I think it's important to sort of like establish community norms regarding like when and how to declare that a paper was fully or partially AI generated. But I think there are some difficulties that arise from like whether or not science should be judged on its own merit to avoid bias against the use of AI, for example. And another instance is misuse of this type of AI technologies. Because we could imagine a situation where some malicious actors try to use this kind of system to inflate publication records to sort of like, and also to game the peer review process. So I think for this sort of like AI-driven technology, I think responsible development is critical, and we need more like community norms and open discussion about these issues. So, so I think the next sort of an interesting direction, like one interesting direction that could go from here is like well, I guess the grand vision is basically like a full automation of AI research, but that's still like I think a little bit far away. But one I guess intermediate goal that could be done is to try to use this sort of system to reproduce existing findings and existing papers in the literature. And one example is Paperbench from OpenAI, where they have this sort of like a benchmark for paper replication. And then another direction could be to have this sort of like a, fully automated AI conference where we set up this AI conference system where like all the papers are AI generated and reviewers are also AI, and we could imagine like we imagine a system where we kind of evolve this conference across multiple generations of these generation and reviewing. And another interesting direction is, how do we go from like this hand design AI scientist system to like self-improving AI scientist system. And this is so in the the first part of the talk, like the system that we discussed was basically hand designed by me and my colleagues. But if we have more, if the AI system, like the underlying LLM's capabilities increase, we could imagine a future where the entire system could be also improved by itself. And in the next, for the rest of my talk, I would like to sort of like discuss some like a first evidence or first glimpse of that kind of system that could be immersed in, at least in the simplistic settings. So to set up the scene, so LLM used to be a thing where you provide a text prompt and you get an answer, but increasingly, it's becoming more like sort of like a reasoning engine or core engine of a more complex workflow, where LLMs can use like a tool, like a web search tool, or like can have access to external memories, or like some sort of planning modules could be provided as an external tool. And then, there are techniques like self-reflection or channel thought prompting to do more like complex reasoning tasks. And we often call like LLM agent, or like whenever there is an LLM, it's been used as like one of the core engines of this complex workflow. And then there are lots of design patterns of these LLM agents. But these are very sort of like a complex workflow and that are hand designed. And if you kind of know the history of machine learning and AI, oftentimes hand design features or hand design systems are often being replaced by sort of like automated or like learned version of it. And this is like one instance of such learned or meta agents, which is we call automatic design of agentic systems, or ADAS. And ADAS is like an AI system that creates basically other agentic systems. And this is again based on open-ended principles, open-endedness principles. What that means is that it has a growing archive of high quality and interesting agents library. So the idea is this meta agent search. So the search space here is defined by code. So like basically each agent can be defined in code, and specifically in Python. And LLM is really good at writing Python or code in general, but especially in Python. So we can ask LLM to come up with what kind of agentic systems that could be developed next based on previous attempts. And we can have this sort of like open-endedness loop where we sort of like continuously collect different kinds of interestingly like different kinds of agents that are generated by this meta agent. And we have this sort of like loop of it keeps like proposing new agents or architectures, and we evaluate the performance of these architectures or our agentic systems based on some task that we prepare. So this is an example of sort of like a performance increase as you kind of iterate this agentic meta agent search on this task called ARC. And as you can see, this meta agent based search sort of like outperforms like all these other sort of like hand designed agentic systems, things like chain of thought, self reflect, or LLM debate. And this is like one example of the best agent that was developed by this meta agent system. We can see that it can produce like a very sort of like a complex pattern of or design patterns of like it has different experts and ensembles and collecting these ensemble results to get the final result. And this meta agent search can be applied to a lot of domains, especially like reading comprehension or mathematics or multiple choice science domains. And this ADAS can also be applied to sort of like different domains in a sense that you develop this you run this ADAS on one domain, say math domain, and you can basically get the best agent from this. You can get the best agent in math domain, then you can directly use that agent to other domains like reading comprehension, and you will see that it's sort of generalized to other domains. So what's next? So we see that the ADAS was sort of like a meta agent system that continuously develops like the agentic systems, but it wasn't really changing the system that produces these agentic systems. And we can think about a version of it where it also changes itself basically. And this is what we call a Darwin-Gauto machine. And we call Darwin-Gauto machine because it was based on Gauto machine. This was sort of like this was like a theoretical concept that was sort of proposed by Schmidt-Huber in 2003, which is sort of like a system that allows self-modification. But it only allows self-modification if there is like a provable guarantee that this edit will improve itself. But in practice, this is almost impossible to predict what kind of edit will provably improve itself. But now with these like large language models, we can sort of like try to do this, but using more like empirical approach, where we can kind of decide what kind of edits would improve itself based on some benchmarks performance. And this is led by Jenny Zhang. This is also using open-ended exploration principles, where it again keeps the growing archive of diverse, interesting agents of these libraries. So Darwin-Gauto machine was evaluated on coding tasks because it basically better coding ability directly means better self-improvement ability because this agent itself is written in code. So again, we can see a very interesting, nice tree of these agent iterations. And as you see, this DGM has sort of like, on average, we can see that the agent performance improves. But the blue line here is basically the best agent performance. And the black line is the most interesting part, which is like the lineage of that best agent. We can see that there are two drops in performance. So basically, this is a result of like open-ended search, because if you kind of drop this agent, we wouldn't have seen this like the best agent at the end. So this sort of like speaks to the importance of like keeping like interesting, diverse agents in the process. And again, this is sort of like evaluation studies where both self-improvement and open-endedness exploration modules were important for the DGM to continue making progress. So takeaways are basically, it's important to go from like a handcrafted to like a learned agent, especially that can self-improve. And principles of openness algorithms really help here. And going back to like the AI scientist, and I think it's still very hard for to have like a self-improving AI scientist, especially because the evaluation of the scientific progress is very hard to verify, and that still requires human sort of like oversight to verify which path would be so promising. And so yeah, that's the end of my talk. Thank you.
Thank you, Yutaro, for your talk. Really, really interesting. My question is about the AI scientist. And I found it really interesting that the paper that scored highly, correct me if I'm wrong, was arguably a negative result. That what you proposed, the hypothesis didn't work out. So I guess that's partly removing human biases on this. But the question's broader of how would the AI scientist consider how their research conflicts with the literature, contradictory results in the literature, if we're looking for some truth beyond, let's just say, novelty of the research idea.
Yeah, thank you. So I think that sort of like depends on like the quality of literature search part of the system. And literature search, it seems very simple, but it's actually very hard to dig in, like especially when you need to kind of find like some like a distant literature that was kind of buried on the internet. And I think one way to sort of like go from like just not only seeking for novelty, but also try to find like contradictory results and stuff based on also the ongoing experiment results that the system is running is basically to have more like a structured representation of the experimental logs or results, not just using like a global markdown node. And instead having graph representation of these like results where nodes could be like results, hypothesis, claims, and edge could be like this result supports this hypothesis, the results is still inconclusive about this particular hypothesis. So I think this sort of like a more fine-grained representation of knowledge base is pretty, I think, important for the next progress. Yeah, thank you.
All right. Thank you for your talk. I think the AI scientist part, that was really interesting to hear. And I think as a technical challenge, it's really interesting. I guess my question is sort of about the use cases for it, because I think science is a very human process. Like we get a lot of insight from actually designing the experiments, talking with colleagues, seeing the failures, trying to sort of iterate. And it seems like that's when you start to sort of automate that. I guess I wonder about kind of the loss of those insights that would happen in the research process and how you might envision this being used or humans being kind of integrated in the loop so we don't lose those insights that we get kind of from the scientific process and the process of actually like doing the research itself.
Yeah, so I think especially with the current capability of LLMs, I think it's more realistic to think of this as more like a co-scientist, where we humans have more intervention with LLM driven research, and we can think of this sort of like a tree search, or like we can like imagine a situation where the system sort of like logs all this tree in which the system has explored, and humans can sort of like if there is like a nice UI or interface to look at these experimental attempts, humans can kind of intervene and hey, maybe this node looks promising, even though the system decides not to pursue, and why don't you explore more? And that kind of like a human-computer interaction user interface, I think, would be a very nice tool to have for the intermediate. Yeah.
My question, and I'm sorry if you already explained this and I missed it, was about the very original idea of the papers for that scientist. So did you pose the question to it, or did it, because it seems to me that that phase of deciding on the question is tightly intertwined with the whole process itself, right?
Right, right. So in the V1 system, the idea was sort of like conditioned on the code template that you provide. So it was very kind of as a narrow exploration. But for the V2 system, we what we did was basically we only provide like a abstract of workshop of that we were about to submit, and so that basically we provide like the very sort of like a big theme of the particular workshop was focused on. And so LLM driven idea generation part was only taking that like a natural language description of the particular workshop theme, and it was directly, and then that part was sort of like, explores different ideas conditioned on that particular workshop theme.
So I wonder if you could take a step back from your particular system and generalize a little bit, right? So as you're thinking about this process, right, and you look across all of the different kinds of science that are out there, right, like what is your sense of how much the sort of work that you're doing and others are doing is saying like, yes, this is possible, and like where is it promising? Where do you think, oh, actually, this is going to take a long time for us to be able to automate other parts of it?
So I think for in some sense, AI research is like, I think, the easier side of this, because everything can be run on a computer. But when you kind of generalize to other science domains like life science or like in biology and chemistry that requires like a wet lab equipment, for these experiments, basically the time to run a particular experiment now can take like weeks, because it kind of depends on like cells evolving, and so I think like a full automation of science for like these life sciences would be pretty hard, and especially bottlenecked by the time that would take for each experiment to run, I think.
And if we restrict ourselves to only the ones that are sort of like on a computer, like do you see any parts of that you don't imagine being automated?
So I think that the what's difficult for the full automation is basically verifying, like, and providing like a useful feedback for the, say, like a tree exploration. And I think if LLM becomes like more powerful to, and if it can provide like a very like a human-like feedback to, say, particular experiment attempts, then I think then we can kind of close this loop of open-endedness search for the full automation pipeline.
Johnny, you get the last question.
Thank you. So actually dovetailing that and referring to the last point you made, this seems very much rate limited by the performance of the LLM, which is right outside of this self-improvement loop, as it were. Do you have any intuition of whether these types of approaches can improve that piece that is actually currently outside of the scope? You're basically getting an LLM, both for the tree search piece of it and otherwise for setting the plateauing of the improvement loop. Yeah, so I think a lot of frontier AI labs are probably trying to use, or at least automate some parts of their research process, where you could apply this sort of like open-endedness exploration, where if you set the objective to be increasing the loss of or decreasing the loss of LLM for post-training, or like then that's basically embedded into the foundational model development. And so so outside of these closed labs or frontier AI labs, I think it's hard to touch on those development of foundational models. But I think within these frontier labs, I believe this sort of like a search process plus some sort of post-training or selection of data sets or selection of reinforcement learning environments to improve the foundation model itself is something that is probably viable right now.
Okay, and we'll end there. Thank you very much.
Thank you.